Hi and welcome to video 10 of this series, Unit 4, Topic 2, Differential Equations for the Senior Specialist Maths Curriculum. In this video we're going to look at example 7, which on my OneNote is my one and only example of logistics curves. There are plenty others in whatever resource you're using, but for now this will be the one that I show in these videos. So in example 7, it reads like this. A remote island with no feral animals is used to set up a breeding population of bilbies. Who cares? Initially, 10 bilbies are released in the island, so that means that the population at time equals 0 is 10. It has an ideal environment and is thought to be able to sustain a population of 600 bilbies. So based on my formula, that means m equals 600. After 2 years, the population has grown to 30, so that means that P2 equals 30. Use the logistics model to find when the population will reach 200, how many bilbies could be taken back to the mainland each of the following year while maintaining the population at 200. So, part A, first of all. We've got a couple of known values, that should say 30, not 3. And we've also got our m values. So you might recall that dp dt is proportional to the population times by 600, or m minus the population, the gap from above and below. Graphically, my solution is going to look like this. I start down here at 10, and at 2 years I'm up to 30. And my scale's bad, but that's fine. And I get to a maximum population here of 600. No, that's 600, and so my model looks like this. It'll build, but then it will flatten out at 600. And I want to know, when do I get to 200? And in particular, when I add a year onto that, what will my population be? Because that is the new number of bilbies that I could take back to the mainland and then be back at 200, and I would just follow this population growth. Now, there's obviously a lot of assumptions involved here. So I have to be careful, but this is my approach to this question, and we'll see how we go. So dp to t is proportional to p times 600 minus p, and that means that dp dt equals kp 600 minus p, which means that the integral of dp over p 600 minus p is equal to the integral of k dt. Now we have to be careful here and do our due diligence and work on this partial fraction. So I want to show what this is equal to, and we'll get something similar each time, but I really should, unless I've got a reason not to, show this work. And so my partial fraction will look like this. 1 will be equivalent to a times 600 minus p plus b times p. If the question varies slightly, then this could change, so we do have to make sure that we do it. So 600a and then plus b minus a p. So therefore 600 a must equal 1, that's just a constant, which means that a equals 1 over 600. And b must equal a, because they must equal 0 together, so therefore b equals 1 over 600. And so I get up here that a and b factor means that I get 1 over 600 times the integral of dp, let's write it like this, 1 over p minus, and that's a plus actually, 1 over 600 minus p dp equals the integral of k dt. And so now I get log of p plus log of 600 minus p divided by -1, because I've got to divide by the derivative of the inside, is equal to 600 times by kt plus some constant c. So I'm going to absorb that 600 in the k and the c. So I get log of p minus log of 600 minus p is equal to kt plus c. which means that log of P over 600 minus P is equal to KT plus C. And that means, of course, that P over 600 minus P is equal to e to the KT plus C. I change the plus C into an A, multiply out, P is equal to A e to the KT times 600 minus P. Expand, and I get that's equal to 600 A e to the KT minus A P e to the KT. Add the second part over to this side, I get P plus A P e to the KT equals 600 A e to the KT. And then I can take P out as a common factor and divide through by what's left, and I get 600 A e to the KT over 1 plus A e to the KT. Or if I multiply through like I did last lesson by e to the negative KT, I get 600 A over e to the negative KT plus A, whichever of those works best. But I'm going to do a little bit of working now to determine some of my values, such as the A and the K, so that I can use those values. So let's start with this point here, and this is kind of going to be a little bit useful to you to know when to interject yourself. So for example, if I jump in here, then I get A e to the KT is equal to P over 600 minus P, and at time equals 0, P is equal to 10. So I get A times e to the power of 0, which is 1, is equal to 10 over 600 minus 10, and that gives me A is equal to 10 over 590, which is 1 over 59. That's my first one, and so now I've got an A value. So using I think I'll use this model, the first model I've got here, I get P is equal to 600, and it's actually, I'm going to write it as 600 over 59 because it's times A, e to the KT over 1 plus 1 over 59 e to the KT. So there's my new model. And now I also know that T, let me just go back up and have a look, T2, yeah, population at time 2 is 30. So I can use that here, and I get 30 is equal to 600 over 59 e to the KT over 1 plus 1 over 59 e to the KT. Now I've got two instances of e to the KT there, so again I probably would have been better using this form here, particularly now that I've found A. So what I'm going to do is I'm going to bring this down to here. It's a bit messy, but I'm just trying to explain to you why I'm making certain choices, because all of this in here, everything I've done here, this is just rearrangement to get to a nicer form. I can pick any point along this journey to find my A or K, whatever suits best. So I'm actually going to use this. A, which is 1 over 59, e to the KT equals P over 600 minus P, and at T equals 2 I get P equals 30. So I get 1 over 59, actually I'm going to rearrange this, I get e to the 2k multiplied by 59, I get 59 times 30 over 600 minus 30. 59 times 30, 60 times 30 is 1800, so 59 times 30 is 1770 over 570. Not a great deal I can do with that, but I can cancel out the zeros, and I'm going to take log of both sides. So I get 2k equals the natural log of 177 over 57, and k is equal to a half natural log of 177 over 57, and so I can use that as my k value now as well, which is going to get out of hand a little bit. So I might actually just make the note that this is approximately equal to, just for clarity's sake, 0.000944, so a slow growth rate, and that's fine, that's what we expected, 2 years to get from 10 to 30, but I'm not going to substitute this in. I'm going to maintain my k. I can deal with the a, but the k, yeah, no. What I'm going to do instead is say the answer to part A is I want to know when does P equal 200. That's the big thing I'm after. So whilst I've created this model, I'm actually going to go back to this one again. This one here is the closest I have to t being by itself, and actually it's going to be important for me to have t by itself. So I get a e to the kt is equal to p over 600 minus p, and I've rearranged this a little bit, so I get e to the kt equals 59p over 600 minus p, and that gives me kt equals log 59p over 600 minus p, and that gives me t equals 1 over k times log 59p over 600 minus p, and I've got my k value there, and I've already substituted in my a value, so I can put in 1 over k log and then 59 times 200 and then 600 minus 200 to work out when I first get to a population of 200. And I've got my k value here, but I'll use the exact value, and it comes out at about, I'll put a little inside, 5.94 years. So it takes 5.94 years before I get to a population of 200. And that's part A. Part B asks me how many could I take away each year. So for part B, I want to know what is the population at 5.94 plus 1 years. That's what I want to know. So I'm going to put that in to my population model, which I did develop, and it has come in useful. Here it is here. 600 over 59 e to the kt over this other stuff, 1 plus 1 over 59 e to the kt. You'll see I'm still too scared to put k in its exact form, so I'm just leaving it as k. But now I can put in my time at 6.94, which I've actually maintained from the previous answer. So I get 600. I'm going to write the decimal form, but I'm using the answer on my calculator. So 6.94 times k being that other crazy number, 59 e to the 6.94 k. And when I put all that into the calculator, I get a population after 1 year from the time it's 200 of 281.685 bilbies. Now, that means, therefore, that I can remove 81 bilbies from the population each year without affecting the population growth or allowing the population to decline. Now, technically, I could probably remove 81 and then 81 and then 82 or something like that, because I have got this number that's pretty close to 82, but it's not quite 82. So if I remove 82 every year, I'm actually going to go into population decline. So instead, because it's not quite 82, I'm going to remove 81, and my population will continue to steadily grow, because after a year I'll have 200.685. So it's a discrete variable. We have to take that into consideration, but we're looking at it in a continuous way. Anyway, that's the end of that problem, and that's the type of problem you might face. You will have to build the model in a lot of cases, not always, but in a lot of cases, so make sure you know how to do the whole process so that you can complete any question. All the best.